All right, so we'll go over our unit exam review here. First thing we covered in this unit was what? Very first day, and I know that was before Christmas. Exactly. Okay, we went over climate. Okay, climate, and the first thing we talked about were the components of climate. Is it important for you to know the difference between the components of climate and the factors that affect it? It is very important. Okay, not only because there could be, like a multiple choice question that says which of the following is not a component of climate or something like that, but also because you are more than likely going to be given a question that involves a geographic location. All right, so let's say a specific city within Canada, and you're going to be asked, describe the biggest factors affecting the climate for this location. Now, if you don't know the difference between the components that are, if you don't know the difference between the components of climate and the factors that affect it, are you going to get that question right? Probably not, all right? Because instead of saying, well, latitude affects the climate of this city, it's right on the ocean, so it is a low altitude. Because it's near the ocean, the ocean can regulate its temperature. These would probably be the three biggest factors affecting its climate, and they would affect it in this way, okay? That would be the right way to answer that question, by the way. Okay, you might instead say, well, precipitation, light, temperature, and wind would be the following. Now that's telling me what the components are, not what the factors that are affecting are. You guys follow me there? Okay, so it's important to know the difference for that reason. All right, so obviously, okay, the components are, okay, temperature, precipitation, light, and wind. Okay, and the factors affecting, okay, latitude, altitude, okay, presence of mountain barriers, okay, proximity to oceans, whoa, okay, and centers of high and low pressure, okay, etc. All right, so make sure you know the difference, and make sure you're able to, at least in some way, describe what effect those factors would have. All right, so if you're saying, you have a, let's say, you're looking at Revelstoke, okay, as a city, which is, up in the mountains in BC, you would say, well, it's relatively high latitude because it's a Canadian city, okay, so it's far from the equator. This affects daylight in this way. All right, being far from the equator affects the length of day throughout the year. It affects the, the angle of incoming solar radiation, and that affects how warm or how much energy the area can absorb. Being at a high altitude means that it is likely to be colder. Being on the the windward side of the mountains means it probably gets more precipitation than something on the other side of the mountains would. Things like that. So don't just list the factors that affect it, but make sure you tell me how do they affect the components of climate. You guys follow me there? Have I essentially laid out how to answer question 2? I can't remember if it's question 2, but it's on there. Okay, make sure you answer it correctly. Okay, be detailed so that you can get full marks. All right, what did we talk about right after that? Did an activity to do with them as well. Climatograms. Okay. Okay, what are you going to be asked to do? Okay, not just what region, what, we talked about them yesterday. What biome, right, what biome it goes with. Okay. Okay, so match with the biome and explain, so you have to be able to read a climatogram. Make sure you look at the scale, all right? Don't just look at how tall the precipitation bars are, okay, or where on the graph the line is. Make sure you actually look at the scale on either side, because sometimes, you can make a really dry place look like it gets a lot of rain if you make the scale really small. Okay, then 60 millimeters of rain is near the top of the scale, and this place looks like it gets tons and tons of rain, but it doesn't. All right, so make sure when you look at the climatogram that you read the scale carefully so that you make the proper conclusion about rainfall and temperature for that area. Everybody follow on that one? Okay. All right. And after that, okay, we had kind of a big lesson, and unfortunately we haven't had a lot of time to talk about applications of the stuff we learned in there, but it was about energy transfers, okay, in the global system. All right. So we started out with that all the energy comes to the Earth in what form? As light. Okay. So light is a form of radiation. Okay. All forms of light, or light in all forms, is radiation. Okay. We see obviously only a small part of the spectrum that we call visible light. All right, so the colors of the rainbow, essentially. All right, there are other parts of the spectrum that also come to the Earth: the ultraviolet rays, the X-rays, the gamma rays. Okay, the infrared rays, the microwaves, all of that kind of stuff. They all come to the Earth from the sun. Okay, we don't see all of them. Luckily, a lot of them are blocked by the atmosphere. Okay, by the ozone layer, and some of them are scattered by the atmosphere as well. We talked about why the sky is blue. Okay, now the big thing we have to remember here about this is the light that does get all the way through and actually makes contact with the Earth. 3 things can happen to it. Okay, what were those 3 things? Those are the 3 ways it could be transferred around the Earth. But before it can be transferred, it has to be absorbed. Right, absorbed, used, or reflected. Okay, and what process used that light? Photosynthesis. All right. If light is absorbed, will that increase the energy of an area? Yes. If light is used, will it increase the energy of an area? Yes. Not necessarily the thermal energy, but the chemical energy, because it's being converted into sugars. Okay? What if it's reflected? No, it won't. What determines how much of the absorption or reflection happens? Okay, what did we call that? Started with A, special word for it. Albedo, right? Okay, the higher the albedo, okay, the more reflective the area is. The lower the albedo, the more absorptive the area is. So the darker colors have lower albedos. That means that they don't reflect, they absorb more. All right, snow has a very high albedo. It reflects everything away. Okay, everybody follow me on that one? Okay, are those going to be important terms if you want to get, let's say, the difference between 4 out of 5 and 5 out of 5 on a question about energy and its interactions with the Earth? Yes. Okay, make sure you know. All right, because there's probably going to be a question that says, tell me about what can happen to light when it strikes, a certain place on Earth. Well, these are the 3 things that can happen to it. You should probably explain what happens in terms of energy for each one. Okay, increase, change, okay, and nothing. And that this is a determining factor between absorption and reflection. Okay, things like that are all important. They show that you understand the relationships. Okay, now after that we talked about the role that the 3 parts of the Earth play in transferring the energy that is absorbed from place to place on Earth. Okay, obviously the equator gets the most energy. All right, what part of the Earth? Well, let's maybe talk about what are the 3 parts of the Earth we're going to talk about here. Not stratosphere, water, hydrosphere. Okay, so we have the atmosphere, okay, we have the hydrosphere and the lithosphere as the 3 parts of the Earth that are interacting in terms of transferring energy. Which one is most important or most involved? The atmosphere. Okay, the atmosphere is the most important part of the Earth in terms of transferring energy from place to place. Okay, because it is the most fluid. Okay, it's the most fluid of the 3. It moves most easily. Okay, and because it moves most easily, what heat transfer process occurs best here? Convection. Okay, so convection is occurring there, and what do we call convection within the atmosphere? Wind. Okay, we'll talk about wind patterns in a minute because that was the next thing that we talked about. All right. All right, within the hydrosphere, is that fairly important? Yes, because the interaction between the hydrosphere and the atmosphere, okay, results in heat transfer by this method, which we said was the second most important way, or the second biggest way, of transferring heat energy from place to place. Okay, we had convection, and convection can move air masses around, but those air masses could contain water vapor, which contains latent heat. When it goes to a new place, it will condense and release that energy. Everybody with me there? Okay, so hydrosphere, okay, also a lot of convection. Okay, because it is fluid, but because it doesn't touch every place on Earth, it doesn't have as big an influence as the atmosphere in terms of transferring energy. All right. Now, the lithosphere. Does it play much of a role? Just for absorption. Okay, its primary role is absorption. Okay, and then hopefully the air above will warm as a result. Okay, but heat transfer through the lithosphere is very slow. Okay, because it happens by what process? Conduction. Okay, and that's that physical, okay, contact and running into each other, okay, of the small particles. Okay, is that ringing a bell for everybody? There's a bit of application stuff on that on the test in the written response, so be ready. Okay, you'll need to know those terms and how they apply. The other way that there's going to be application of this, if you looked at your final exam review, there was a question about designing a device or something that could keep something cold or keep something warm or something like that in the Unit 4 review. Okay, and that's what we normally do if we have time in this unit. We build a solar heating device. Okay, you build a device that will capture energy and transfer it to a vial of water. Okay, we try and raise that vial of water's temperature as high as possible during the test. That means we have to be able to harness radiation, okay, as a form of input energy. We have to be able to convect and conduct that energy quickly into the water. All right. The opposite is true if you are trying to insulate something. Now, if you're trying to insulate something, you're trying to radiate or reflect and keep all the energy away. You're trying to prevent convective energy transfer into the material, okay, conductive energy transfer into the material. So yesterday we just briefly talked about how the insulation, the fiberglass, the pink stuff that's in your walls, okay, is similar to snow. All right. When snow falls, we said it's highly insensitive because we were talking about the boreal forest biome there, the taiga, and we said that lots of animals use the snow as an insulator. If you build a quinsy, you can use the snow as an insulator because in between the interlocking snowflakes is trapped air. All right. Now, there's air in here. Air in and of itself is not a great insulator. But if it can't move, what can't happen? Okay, can't get warm or cold. If I'm inside the quinsy, okay, I'm obviously making it warmer inside, but it's cold outside. If the air from inside can make contact with the air from outside, will energy transfer? By what process? Convection. Okay? With the air being trapped in between snowflakes or in between glass fibers like it is in the walls of your house, it can't move. And as a result, convection cannot occur. No convection current can get set up in here because the air is no longer fluid. It is interrupted and can't flow from place to place. That's the principle behind most insulative materials. Okay, you look at, like if you put on a sweater, right? What's wool look like when you look at it really close? Like it's a random kind of intertwining of threads. Is there air trapped between the threads? Okay, that's why sheep stay warm in the winter. Okay? That's their hair, right? You give them a buzz cut when you harvest the wool off of them, okay? But it insulates them because it traps air and it does not allow it to move. Now, We use lots of synthetics that do the same thing. Okay, thinsulate is essentially like synthetic wool. All right, ducks and geese have a layer of down, special feathers underneath their flying feathers. Okay, that trap air and don't allow it to move, and that keeps them warm even if they're wet. Okay, which is why if you buy kind of high-end sleeping bags and jackets and stuff, you get them filled with down. Okay, they're some of the warmest clothes and sleeping bags that you can get. All right, it's a very insulative material. Everybody follow me there? Okay, but all of them do exactly the same thing. They prevent convection currents from occurring. All right, now that works as long as they're nice and fluffy. All right, if they get compacted at all, then those air spaces are gone, and now you're in straight contact with the material underneath or around you. Then what process will happen? Conduction. Okay, and you'll start to lose energy through conduction. Everybody follow me there? Right? That's why even, if you're kind of like a hardcore outdoorsman, you usually have some sort of material that you sleep on that's between you and the ground. If you sleep directly on the ground, you're going to lose heat by conduction to the ground. All right? So you usually have at least some thin layer of foam, okay, that is between you and the ground. Everybody follow? Okay. Is an air mattress good if you want to stay warm? Because an air mattress doesn't trap the air, does it? Can the air within an air mattress move? Yeah, okay. You're laying on top of the air mattress, the air inside moves. Okay? It takes and it follows the second law of thermodynamics. It goes from you, hot, to the ground, cold, and it just goes like that. Okay? Very quickly you can get cold while sleeping on an air mattress. Okay? Everyone follow there? Okay? So that's sort of the idea that we work on when we're trying to insulate or prevent conduction. All right, so we trap air in that way. Does that also prevent conduction? Yeah, because sure, there's glass fibers that are in contact with your inside wall and your outside wall, okay? But glass is actually a poor conductor of heat, all right? Lots of materials are. Metals are usually good conductors of heat, all right? So that's typically why we don't use metals, okay, when we want to insulate something, all right? Because they're usually good conductors of heat and they'll push the heat through very quickly. What would be even better if we could make it and maintain it than this trapped air? Convection can only occur if there's a fluid, air or liquid, in between the two walls. What would be even better than trapped air? No, not, well, trapped water, but it would be heavy, right? And if it ever got out, it would rot your walls. But, similar, right? It's trapped, it can't move. Nope, no air at all. What if you could make a vacuum in between the two walls? There's no conduction because there's no contact between the inside and the outside because there's no material there. Okay? There's also no convection because there's nothing to move. There's no particles to get moving in a circle. All right? And you don't have to worry about radiation if you paint the inside walls what color? White. Reflect all the heat from inside back to you. That's why most houses have light-colored interior walls. Okay? It also makes them brighter, but it also reflects back most of your energy. Okay? Where does your house lose the majority of its energy? Where do you think? No. Where does it to the outside? When your furnace is running, it's maintaining the internal temperature of your house. What part of your house lets out the most energy? Windows. Windows and doors let out the most energy. Why? They're the thinnest. Okay? It's just a thin layer of glass. All right? Now usually it's two panes of glass. What's in the middle? Sometimes, but usually there's also a dead air space. That's usually a vacuum in between the two panes of glass. Okay? If you get low E glass, sometimes they'll throw something like argon or something like that in there that is even better. Okay? That prevents convection from happening. But windows and doors are still the thinnest parts of the walls of your house, and that's where the majority of your heat loss comes from because it's much easier to transfer through thinner spaces. Right? That's why most houses now are built with 2x6 construction on the outside. That means 6-inch thick walls. All right? Back well before I was born, lots of houses were built with 2x4. Okay? Well, your walls lose a lot more energy. Okay? I had a house when I lived in Lloydminster that was 2x4 construction with newspaper insulation. Okay? I didn't want to go to bed with wet hair near the wall because I could wake up in the morning with my hair frozen to the wall. Okay? Yeah. Another 2 inches makes a big difference, especially when your house is not filled with newspaper insulation, okay, which made it a fire trap as well, okay. But yeah, so things to think about. That's what people used to use before fiberglass was developed. They crumpled up newspaper, or shredded newspaper, and filled walls with it, okay. Does it trap air? Yes, it does. Okay, I'm not saying this to sound cruel, but homeless people will often use crumpled up newspaper stuffed in their coats to stay warm on cold days if they're living on the street. Okay, it keeps them warm because it creates another barrier of dead air between them and the outside. Okay, so they stuff that in their jackets, helps keep them a little bit warmer. All right. Is that everyone kind of getting the idea there? Okay, so you might be asked, and by might I mean will be, asked to apply your knowledge of heat transfer to some sort of practical application like that. How would you, prevent radiation or capture radiation or prevent conduction or utilize it, prevent convection or utilize it? Okay, it'll depend on the situation. What about for radiative energy? If you want to keep it out, what do you have to do with it? You have to reflect it away. What do you need for that? Light colors. Okay, if you want to absorb it, you want dark colors, right? Okay, so think about this. You want to have something that'll heat water on a sunny day. Do you want it to be clear, white, or black? Black. Okay, you want it to be black because black will absorb the most energy. Everybody follow there? Okay, so things to think about. Okay, practical application stuff. All right, so that was the third one. After that, we talked about wind patterns. Okay. Wind patterns, okay, are the result of 2 things. What were they? Convection is one of them, and the rotation of the Earth. Okay. Okay. So wind patterns, the prevailing winds anyway. Okay. Remember that diagram we had? Okay. Prevailing winds, okay, are a combination of convection and the rotation of the Earth, okay, which we called the Coriolis effect. Make sure you know that term. Okay, the Coriolis effect. Now, the jet stream was another important wind mechanism that we talked about. Okay, the jet stream was that high altitude wind, okay, that could transfer air masses, okay, or transfer latent heat and things like that from tropical areas to northerly areas because it's always moving up and down, okay, in each hemisphere. All right, and that movement up and down means it's bringing air from different places. We showed you that weather map where we talked about how that jet stream could make unsettled weather in certain places and other types of weather in other places. All right, so make sure you look at that wind patterns lesson. It kind of ties in with lesson 3, especially with this convection and the Coriolis effect. Okay, remember that diagram we had of the Earth, right, where we said hot air rising, okay, and then it starts to move north. Okay, this air moves south. All right, but as the Earth spins underneath it, okay, and that pattern happens, it makes it seem like the winds are being deflected this way. Okay, but at this latitude, they're deflected this way, and as they come from the pole, they're directed like they are at the equator. Everybody follow that one? Is it ringing a bell? Okay, we talked about it right before Christmas. Now, what do we call these winds here that were the easterlies at the equator? They had a special name. Anyone remember? Trade winds, right? Okay, these were the westerlies and these were the polar easterlies. Okay, those could be like multiple choice type things. All right. Okay, and then after the wind patterns, we talked about specific heat capacity. Okay, how am I going to ask you about specific heat capacity? Yeah, there'll be certainly at least one problem-solving question where you'll have to use E equals MC delta T, okay, manipulate and solve a problem for it for sure, okay, but there could also be some multiple choice questions that might ask about some applications of it, right? If you want something that acts as an insulator, you don't want its temperature to go up very much. You would probably want something with a high specific heat capacity because it takes a lot. It can absorb a lot of energy without changing its temperature. All right, things like that. Also, specific heat capacity had to do with one of the important factors affecting climate, and that was proximity to oceans. Okay, because water has a very high specific heat capacity. All right, and so if your air temperature begins to drop and it drops below the temperature of the ocean, the second law of thermodynamics takes place. Okay, energy flows out of the ocean and into the air, but because the ocean is made of water, obviously, okay, and water has a high specific heat capacity, a lot of energy can move out of the water without the water changing temperature very much. Everybody follow? Okay, that was how this regulated temperature in maritime and kind of Pacific areas. All right. There could also be some multiple choice questions simply about what C is, okay, maybe units, okay, stuff like that. So make sure you just review those notes quickly. Okay. 6, latent heat. All right. So latent heat, obviously, again, you got to know how it's part of energy transfers in the global system because we've already talked about that part. But bet that there will also be a problem to do with this, worth between 6 and 8 marks. What is that? Right, the heating curve of water. Okay? It shows us what happens to the temperature of water as we add energy to it. Okay, so down here, okay, this graph is energy and temperature in degrees Celsius. Okay, as we add energy to ice, it increases in temperature and then eventually begins to melt. Okay, once it's completely melted, the temperature goes up again until we get to 100 degrees. Till we get to 100 degrees Celsius, okay, then it changes state again, and then the steam heats up, okay, after that. Now, do you need to know this by heart? You do, okay? I'm not giving you that shape on the test. I'll give you all the formulas to do with it, but I will not give you that shape. I expect that you know when water boils and when ice melts. Okay, I don't think that's an unreasonable expectation of you. All right, I expect that you guys know that. Now, what formula do I use anywhere where temperature is changing? E equals mc delta T. All right, so you use those in each of those places, but what is different about how you use it in each one of those places? Alicia? Right, you use a different heat capacity in each place. Remember that ice, water, and steam all have different specific heat capacities. All of those numbers will be given to you on the test or in the question as you need them. All right. What formula do I use here? MLF equals MLF. Okay, latent heat of fusion. That has to do with whether you're going from water to ice or ice to water. Doesn't make any difference. Okay, and what about up here? MLV. Okay, and again, LV and LF will be given to you as values on the test. Okay, and then the last thing we talked about was biomes. And you know that there's going to be multiple choice questions with pictures and descriptions and a climatogram that you will have to match with a biome. Okay, that's it. Is there very much on this test? No. Okay, because there is so much less content on this test, okay, this test is a real opportunity to bump your grade up before the final exam. All right, spend as much time studying for this test as you have all of your others, and I guarantee you'll do better on this test than you did on all the others, because you don't have nearly as much stuff to practice or remember. Okay, so you will study those fewer things better. All right, and as a result, you will do better. All right. If you take this test lightly and don't prepare for it, you are going to lose out on an opportunity to improve your mark. All right, and I would assume most of you would like a nice high mark before going into the final exam. Okay, not that the final exam is brutal, it is not. Okay, but there's a lot of stuff on the final exam. Okay, and obviously that means that it makes that's what makes it difficult, is the volume of material, not the level of difficulty of the questions. All right, to assuage your fears maybe a little bit about the final exam. Not everyone shares this thinking, but it's my thinking on a final exam. The final exam is not the place to ask the hardest question I can think of, so I don't. All right, the questions on the final exam are not as hard as the ones that have been on your unit exams. They're usually a little easier because there's so much more material. Okay, so the level of difficulty of the questions on the finals probably either equal to or less than, never harder, okay, than your unit exam questions are. All right, but obviously there's a lot more material on the final, and that's what presents the difficulty. No. No, because it's not all multiple choice. Okay, your final exam is just like a unit exam, it's just longer. Okay, there's 50 multiple choice, and right now I think there's 15 written, or 12. I can't remember which now. I'm still toying with it. I haven't printed it yet because there's still some things about it gave myself some editing time. Okay, so it'll be between 12 and 15 written, but there's definitely 50 multiple choice. I've finalized that. Okay, so it's very similar to a unit exam, except a little bit longer. Oh yeah. In fact, you'll get a new periodic table. Okay, on your final exam, you'll get a new periodic table. It'll be small. Okay, it won't be as big as the one you got in class. It'll be smaller. I will have on that periodic table highlighted the special molecular elements. Okay, the ones you would have highlighted on your periodic table are highlighted on the periodic table you will get with your final exam. All right, there's a table of polyatomic ions on there. It's the same periodic table you had before. There's a solubility chart on it. Okay, there's a page that is just constants and formulas. All right, so you'll have, at least the way I'm thinking of setting it up is you'll have kind of the cover page with the instructions. When you flip that over, on the back of that will be where you'll fill in your multiple choice. So you'll probably just take the cover off. Okay, that's where your multiple choice answers will go. Behind that will be your solubility chart, constants and formulas, and on the other side of that page will be your periodic table. So the first two pages you'll just take right off. All right, the rest of the test, multiple choice, and then your written response. Which should you do first? Please do the written response first. If time becomes a factor, it shouldn't, but if it does, you definitely want to have all the written done. They're worth way more marks. Okay, the test is out of over 100. All right, and there's only 50 multiple choice. All right, get the written done first. It's way easier to rush the multiple choice than it is to rush the written. Okay? Everybody with me there? Realistically, the 50 multiple choice questions should not take you more than a half an hour. Probably less than that. Okay? I would think that on average you could be doing between 2 and 3, maybe even more than that, multiple choice questions per minute on that test. Okay? I mean, there's one or two where you have to do a little bit of math, but it's not difficult math. All right? And there's a lot of them where you'll just know the answer right away and you'll be done the question in 10 seconds. All right? So I think on average you should be able to do between 2 and 3 multiple choice questions per minute. All right? So if there's only a half an hour left on the test, okay, and you've got, still 3 written response questions, you're probably a little bit behind, but you can probably rush the multiple choice. Finish the written first. It's the most important part. Okay? All right, I think I've talked enough about the final exam. I've got 2 more days to talk about that. Okay? Did I give you guys the unit exam review yet? No, I gave you the final exam review. Okay, I'll give you the unit exam review sheet here, and then you guys can work on that. And if you have, are there any questions right now about this unit exam? Okay. Okay, guys, just a couple of quick details here about your about this unit exam here. You got 25 multiple choice questions. Okay, on various things, the biomes, the water cycle. Okay, again, a lot of the stuff we talked about in lesson 3 there with the heat transfer and global energy transfers and stuff like that. Okay, some latent heat stuff, some specific heat stuff, and then there are 9 written. Okay, and that is, some latent heat and energy transfers, some specific heat, energy transfer again. Okay, lots of energy transfer stuff, wind patterns, climate. Okay, so you got some idea there of what I'm going to ask. So there's 9 written and there's 25 multiple choice. the whole thing is at a 73. So there's 48 in the written.